Hello, my dear boys. Hope all of you are well and hope you are watching online classes. You should input your roll number into the comments box because it will carry your CA SBA marks. In our previous class, we are discussing about thermal expansion of matter. It is a continuing class. In our previous class, we have discussed about the expansion for solid. In today's class, we will discuss about the expansion of gases and expansion of liquid uh, by applying heat. Okay, this is your school and this is your school program. So this is our physics lecture chapter 6, effects of heat on matter, and this is our lecture 5. Okay, and this is your teacher Sajib Bishwas, lecturer physics, department of physics, St. Gregory's High School and College, and this is my image. Okay, then today's topics. Today we will discuss on expansion of liquid. It has two parts. Number one, apparent expansion, and number two is real expansion. The other topics is relation between real and apparent expansion, and the last topic is expansion of gas. Let's discuss about the topics. Our first topic is expansion of liquid. We know that liquid have no length or area. It have only volume. So expansion of liquid means its volume expansion. So we get two type of expansion. One is apparent expansion and number two is real expansion. Basis of the applying of heat. We know that if we liquids we liquids we liquids are in a container. So if we apply heat into the container first container will expands and then liquid will expansion. Okay, so our first topics is relay apparent and real expansion. And what is apparent expansion? Apparent expansion is that the expansion of liquid without considering the expansion of the container is called apparent expansion. Okay, if we considering if we are not considering the expansion of container uh, containing liquid, then it is called the apparent expansion. And if the expansion of liquid is measured considering the expansion of the container is called real expansion. Okay, now we will discuss about the example and relation between real and apparent expansion. You are watching a figure here. If we heat, if we applying heat to, the liquid containing bulb, then first the container will heated and expand. So the level of water becomes the level of become the level of water becomes uh, reduce and it will mark as B, and then after some time uh, the liquid will also expand, and the whole liquid will expand up to the mark C. Okay. Okay, here if VB is denoted as expansion of glass bulb, VL is real, and VA is apparent expansion, then we can write VA. VA means apparent expansion, VL means real expansion, and VB means expansion of bulbs. So the relation between these three term is VA equal to VL minus VB. We can also write it as VL equal to VA plus VB. This is the very important relation for our mathematical problem. Then our next topic is expansion of gas. Expansion of gas. So expansion of gas is very interesting because it has no definite shape or volume. It covers the volume of a container by applying pressure. Liquid or solid cannot be compressed easily. So volume and pressure is very much important for expansion of gas. I am repeating, expansion of gas is very interesting because it has no definite shape or volume. It covers the volume of a container. So by applying pressure, we know that by applying pressure, liquids or solids cannot be compressed easily. But volume and pressure is very much important for expansion of gas. So in this slides, we will get the relation between coefficient of volume expansion and temperature. From the ideal gas equation, we know that PV equal to nRT. Here, P is the pressure of the gas, V is the volume of the gas, mainly volume of the container. Here N is the number of molecule of gases, R is called the uh, uh, R is a constant, it is the gas constant. The value of this constant is 8.314 joule per mole per Kelvin, and here T is the temperature. At a certain temperature, if the volume of a gas is V1 at temperature T1 and the volume V2 at temperature T2, the coefficient of volume expansion beta P of the gas, then we can write from our previous equation is beta P equal to V2 minus V1 divided by V1 whole divided by T2 minus T1. Okay. Again, we know from our ideal gas equation PV equal to nRT for temperature T1 and volume V1, we can write this equation as PV1 equal to nRT1. This is our equation 2, and for temperature T2 and volume T2, we can write PV2 equal to nRT2. This is our equation 3. Equation 3, subtracting equation 3 by equation 2, we can get P into V2 minus V1 equal to nR into T2 minus T1. Now, dividing the left side by PV1 and right side by nRT1, we get V2 minus V1 divided by V1 equal to T2 minus T1 divided by T1. By cross multiplicating, we can write V2 minus V1 divided by V1 divided by T2 minus T1 equal to 1 by T1. Okay. Then comparing equation 1 and equation 4, we will get beta p equal to 1 by T1. So we can see that the coefficient of gases are not constant. We can see that the coefficient of gases are not constant at all. It is the reciprocal to the temperature. It is the reciprocal to the temperature. If temperature is increases, then the coefficient of gases is decreases, and if the temperature is decreases, then the coefficient of gases is increases. So boys, this is all for today. For your CW and HW marks, here for this lecture CW is whole lecture, and HW, for HW you should write all definitions I have discussed already in this lecture, and the relations among the different term of this lecture. Okay. So thank you boys, thank you. Hope all of you are well and you are staying at home. So stay home and stay safe. Thank you.